This is kind of a classic problem that you find in almost every calculus book, this sort of a thing. First, let me draw a picture and add a few pieces, because with this information that's written here, there's not enough to actually work with. So I'm going to draw my wall. And this wall, I'm going to say, has height y. And I have this 16-foot plank here. So I know that this is 16 feet. And obviously this is going to be x. And what's happening, you think of a little guy standing here. Yeah, that's a guy. And he's got a rope or whatever, and he's pulling it up. He's pulling this end of the plank up. And we know that it's coming up at 1/2 foot per second. So that's how quickly the rate of change in reference to y, or of y with respect to time. So actually what I just told you was that is dy dt. So the question is, how fast is the end of the plank sliding around the ground? So how fast is this end right here moving, and it's moving in this direction, because obviously I'm pulling up on this end, so this is moving in that direction, when it's 8 feet from the wall. So at some point I'm going to be here at 8 feet, and how fast is it moving in that direction at that exact point? So it's asking for the rate of change in this direction, so it's actually asking for dx dt. So this is what I need to actually try to find. So I need to set up some relationships here. I know just from Pythagorean theorem I have a right triangle here. So if I think of this as x and this is y, I know that x squared plus y squared equals 16. That's kind of obvious. Now if I know I need the derivative with respect to t. I'm looking for dx dt. So I'm going to take the derivative with respect to t. And when I take the derivative of the whole thing with respect to t, I will get 2x dx dt plus 2y dy dt equals 0. I mean, literally, I'm taking the derivative all the way through. So now, because I'm asking for dx dt, I can solve this for dx dt. And I may want to go ahead and put in here dy dt is a half. So I think I'll do that right now. So I'm going to say 2x dx dt equals 2y times 1/2. Oops, I'm sorry, that's not equals, that's plus. Equals 0. Now, it has these units of feet per second. I'm going to leave them out for right now, and I'll slide them in here in just a second. These 2's are going to cancel. So this is then telling me that dx dt must be equal to a negative y over 2x. Now notice, in order to actually find the rate of change along the x-axis with respect to time, I need both the y-coordinate and the x-coordinate. Well, we have the x-coordinates because it said when it's 8 feet from the ground, so that's x. So if I go back to my original function, I know it's x squared plus y squared equals 16. And I know that x is going to be 8. Oops, this is 16 squared. I just kind of noticed that. Because Pythagorean theorem, y squared plus x squared equals the hypotenuse squared. That should have been squared. Didn't make a difference. It's still 0 here. It's going to make a huge difference here. Okay, x is actually equal to 8. So this implies that y squared equals 16 squared minus 8 squared. So see, this is going to imply that y squared equals 16 squared is, this is 256 minus 64, which is 192. So that would then imply that y equals the square root of 192. And the square root of 192, let's see, I can do that as an 8 squared times 3. So the 8 would come out, that'd be 8 root 3. So that's the y value. So if I substitute these coordinates back into this equation right here, what I have is the rate of change of x with respect to t when I'm 8 feet away is a negative 8 root 3, that's the y coordinate, divided by 2 times x is 8. Well, these 8's will cancel, and I will get negative root 3 over 2. Now, these units here, we need to take a look at these units because this should be feet per second. Is that what we actually get? Well, dy dt was in feet per second. So I know these units will carry down. I will have feet per second here. I also have these units when I put these coordinates in. The y coordinate is in feet. The x coordinate is in feet. So I would have actually had feet here and feet here. Those would have canceled, and I still would have ended up with the right units, feet per second. Now notice here, it's kind of important, you see this negative sign. What all this negative is telling you is that I'm heading in this direction. That this distance is shrinking. If I were to have this board way up here and be pushing it downward, then this rate of change of y would be a negative 1/2 in the opposite direction. As I'm pushing it downward, this end would be moving outward, and then this would have been a positive root 3 over 2 when it's 8 feet from the wall. So this negative is important. It's actually giving you a direction.